So thanks for the kind introduction. My name is Maximilian Kirschhock. I'm a postdoc at the Weizmann Institute of Science. And I want to start my talk with a seemingly simple question. How did I get here? So like all of us this morning, I had to find my way out of bed, but also out of the apartment and to the train station. Then I traveled some distance via train, and then once I was here, I had to find my way to the stage. So all in all, I traveled quite some distance, all the while having a goal in mind, the stage, which I could not see from my bed, for example. So if you think about it, this seemingly simple everyday task is quite complicated after all. And even more so in times where there wasn't Waze or Google Maps. So still, people back then knew how to navigate. As a neuroscientist, I want to know how our brains enable us to do these complicated tasks. And as a biologist still at heart, I also want to know how different animals can do this. So let me tell you how the field of brain research has typically tackled these questions. So typically a small animal, like a rat or a mouse, is placed in a small box where it's running around looking for food that is scattered on the ground. Here you can see a rat in a 2x2 meter box. And I hope you can see that once I start the video, there is a gray line following the animal where it has gone. So while the animal does this, neuroscientists then record brain activity in the hippocampus of the animal, which is the so-called navigation center of the brain. It's a little bit like holding a microphone to a neuron and then recording whenever it becomes active. When it becomes active, it fires an action potential, and the place where an action potential is fired is indicated in red here on this map. So if we do this for a while, we see that the animal runs all over the place, but the neuron only fires action potentials in a very confined space of this box, indicated here by the warm colors. Because of these properties, firing or becoming active only in a certain place of the arena, this kind of neuron has been called a place cell, and the place where it fires is the place field. And different such place cells have different place fields. So while a green neuron would have its place field here, a red neuron would have a place field somewhere else, and accordingly a blue and a yellow neuron would also have their place fields. Of course, the hippocampus does not consist of only 4 brain cells, but many of them. So that all in all, the hippocampus covers the entire box, this entire arena, by partly overlapping place fields. Like this, the animal can then know where it is. When, for example, the blue and the yellow neuron are active together, then the animal must be here. And because of this property, the hippocampus has been said to contain the so-called cognitive map of the brain. So if you find this finding quite elegantly solved, quite fascinating, then you're not alone, because in 2014, this has been awarded with a Nobel Prize. Other than place cells, the hippocampus also contains other specialized cell types that code for other spatial variables, like the heading direction of the animal, barriers, or the scale of this environment. So brain research has told us that the hippocampus of the brain contains a representation of space from which we can read, from which the animal can then navigate. However, animals and us humans, we don't live, let alone navigate in small boxes. But as in my opening example, we travel quite some distance in complex environments, which are three-dimensional, partly occluded, and where you cannot always see where you're going. So there seems to be a kind of a disconnect between what is typically studied in the lab and what's happening in the real world. My postdoc aims at bridging this gap, as I want to bring the laboratory science into the real world. The dream for me would be to record these kinds of place cells, for example, or other specialized cells, but out in the real world. So let me briefly tell you how far I have come, or how close I have come to this dream. So first up, I need an animal that is known for navigation. And this is where I introduce to you the Egyptian fruit bat. That's the animal model I'm working with. These, I think, quite cute bats are native also here to Israel. So most of you have probably seen them flying around at night. They are quite big. They have a wingspan up to 30 centimeters. So they can carry a lot of weight. And more importantly, they're expert navigators. they will find the same fruit tree that they prefer for some time while it bears nice fruit, even 15 kilometers away from their cave. And so the different colored lines here in this plot is the different flight trajectories night and again. And as you can see, these bats do not wander around looking for the fruit tree somewhere. No, they straight beeline to where they want to go and then come back over a course of many, many kilometers. Right, so now that I have an animal, which is good for navigation, I need to be able to record not only where it's going, but also its brain activity. And for this, we joined forces with a very talented engineer in Jerusalem, and we developed the so-called neural loggers. A neural logger, which you can see here, is a tiny device that can record and save a whole bunch of behavioral variables, like the localization or the vocalizations of the animal. And more importantly, it can also record brain activity wirelessly. So it's a little bit like holding 64 microphones inside the brain. Together with a battery, this device is still less than 10 grams, so actually the bats can carry it around while flying. And because all these sensors usually take up a whole room of scientific equipment, what we ended up here with this logger on the bat is some kind of flying laboratory. Now, going from the very small to the rather big one, we were lastly needing an environment for the bats to fly in. And this is a video of what was happening behind the Weizmann Institute campus. Over the course of 1.5 years, we have built a huge flight maze specifically and only for the bats to fly in. In this top view from a drone and also below in the schematic, you can see that we erected a overground tunnel system of many interconnected tunnels. And in red, here you can see landing platforms for the bats to, well, land on, but also where they get their food reward. So they have lots of options to land and fly in between these platforms. And just to give you a sense of how big that is, this black square that I put in the bottom is not some kind of schmutz that I forgot on the slide. No, it's actually the size of a typical navigation setup. So now that I have everything, I have my expert navigators, tiny recording equipment, and a huge maze, it was time for me to put it all together in order to, come close to my dream. So last year I started running experiments, and here you can see the star of the show. This is one of my bats carrying the logger or a training logger on its back and hanging, chilling on a landing platform inside the maze. So the most pressing question we had in the beginning was, of course, are place cells even real? Or would I have to be the one to decry a Nobel Peace finding as wrong? So as you can imagine, I was quite anxious to do these plots. And here you can see the outline of the maze. And in gray, just as in the previous example, I have the trajectory of a bat flying inside the maze for around 2 hours. Then I recorded neuronal activity in the bat's hippocampus, and the responses of one such neuron are coded in red here. And as you can see, this particular neuron has 2 of such place fields, so it fires only in a very confined space of this maze. So the day was saved. There is classical place cells. Nobel Prize finding is not wrong, and I can continue with my work. And there's other open questions that can be addressed now. So for example, I told you about these other specialized cell types. As you can imagine, in a huge environment like this maze, there's lots of spatial features to be represented. So there's lots of things to look out for. And on a more meta level, the question would be, such huge environments, are they encoded by one big cognitive map, or will they be made up of many other smaller parcellated maps? And lastly, the open question is also, will there ever be a Nobel Prize for bat research? Who knows? Right now, I'm working on answering all those questions. With that, I want to thank the lab that has welcomed me very warmly here in Israel, and also the Israeli Foundation for funding this. And last but not least, I want to thank you for your attention. Thanks.
Thank you.